So now we are officially in session. Welcome everybody once again. And what we'll do basically is to start our course right now. This course, we all know, is a design course. In this course, we cover across technologies. That's LTE, UMTS, and DAS. We explain during the by the end of the completion of this course, you guys will able to understand and also do the design of overall design of this course of radio network, both macro sites and DAS sites. So how we have devised this course basically is we have different chapters of course. Will give you a more in-depth understanding of what this course is trying to do before we move on to the first information part of this course. So this course basically provides practical knowledge about cellular design network. What we are doing over here is basically without going distributing our course based on technology that this is only for LTE or this is only for UMTS. We are overall putting in the end-to-end design process. I can hear somebody's background noise. Okay. We okay. End-to-end design course. So basically what this course is doing is providing you the design knowledge for LTE, UMTS, DAS networks end-to-end. So during the course, you will able to see both macro and DAS network. As in this slide, you can see this is the overall framework of how this course will go. We have if you have a basic understanding of any cellular network, it has macro sites, it has DAS sites. DAS sites have been in deployment lately, but it is a very booming field right now. But either macro site or DAS site, it has some basic body of knowledge which is shared between the two. And then there's some things which are different between the two, like the process itself is different, the design tool which is used for DAS or macro site is different, the how we prepare the RFDS or design sheets. What is RFDS or design sheet we will learn during the course of this session or the course of this whole training course one. So what is RND-CIQ we'll learn, but what is the process followed to reach the RFDS or RND-CIQ in different scenarios, if the site is 2C or 3C, or if it's a DAS site, if it's a DAS 4C site, or if it's a macro 4C site, how many sector it has. So and what tools it requires. It requires design tool for if it's a macro, it's a tool, and we'll see how a tool works. We'll see how Ibwave works. We will not have the hands-on for a tool or Ibwave because it's practically not possible in this budget of the course. But we'll have the sessions and videos to explain step-by-step process what ATOL is used and how ATOL is used, and there are videos in which this ATOL training is covered and Ibwave training is covered using videos. And then we can have later on if more detailed sessions which will be out of this course hours. But in this course objective, you'll completely able to understand how ATOL works, what is its role, and how to use basic functionality of ATOL and Ibwave for DAS sites. So what this course is basically doing is it's getting you RF basics, it is giving you design concepts, it's getting you introduction and very close to hands-on knowledge, but not hands-on knowledge, but of planning tools. You will know how to prepare RFDS for any macro, DAS, 2C, 3C sites, and the RND-CIQ and how the RND-CIQ is prepared and what is their role in this overall design process. So so far, any of you guys have any questions? You guys can type or raise your hand. Usman, do you have any question? You can type, Usman, or you can just put your question up. Yeah, put your question up.
Okay, my question: do we need to install any softwares in order to do something or understand it properly? The reason I'm asking because I actually worked the night shift. I just woke up. I just like 2 minutes ago I did the registration and I'm like totally blank. So I haven't even gone through the prerequisites that you sent.
Okay, no, you don't need to install any softwares. So you don't need to install any software for this course. So unless until just make sure the Citrix standard platform on which we are conducting this training is working fine on any of other machines if you want to use it later on. That's it, nothing else. Okay. So what we have is basically in our overall that is our goal of this training. Before we jump into the end-to-end process of this training, there is a very important slide of end-to-end process. Alila Ari has a question. What is this question? Is there any way to get a tool or Ibwave for hands-on training? No. For me, no, there is no. Their licensed software, their cost runs into thousands of dollars. I don't know otherwise anyway, unless somebody is willing to purchase them. Okay, so these are the 5 fundamentals outlines you can say which this course will be delivering. Before I jump into the process or the end-to-end process, how this course is designed based on the workflow, before I explain that, I just want to refresh in your guys' memory what is the UMTS architecture, what is the LTE architecture itself is. And so in a cellular network, there are many domains. There is a UTRON or the radio network, or there's a core network. So radio network and the core network are always there. Either you're talking about UMTS, LTE, or GSM, or CDMA. Any technology, which is a cellular technology, has a portion of the core network and the radio network. What happens basically is in different technologies, UMTS or LTE, the component changes between core and radio network. The jargon changes. Jargon, when I say jargon, it means in GSM the node B was in GSM it was called BTS, radio base station. RBS and UMTS is called node B. In LTE it's called eNode B. So these there used to be a RNC in UMTS and the BSC in GSM, but no more there is any central controller in that sense in LTE, but there is still something called MME, which we'll look into. So what, as an RF engineer, if we look at LTE or UMTS, we will see the region which is highlighted in red is our domain. As an RF engineer, we should know about all of those nodes. The thing is, if I try to explain you how, if you're able to see this portion, basically, let me put on my pointer on. Okay, you see this portion is basically, which is marked in red, is RF. This portion is the main domain of RF engineering. This is called air interface. Okay, this air interface is basically what RF engineer, most of his job is about. As you move away from this air interface, you will find that we should know about node Bs or eNode Bs. We should know about MMEs and RNCs. So what basically the job of an as an engineer is to able to design the air interface, which is between the UE and the node B, or the base station. We should know how the node B works, what kind of node Bs are there, what are the capacity constraints. Note these two words. There is a what is baseband capacity and what is radio capacity, because these two words you should understand very well. And during the course, during this course, we'll be learning what is baseband capacity and what is radio capacity and how it's dimensioned, because this is an important part of RF engineering. And how the RNC is dimensioned is also part of RF engineering. So this is basic explanation. For many guys, they already know it. As I said, for few guys, this is a new thing. But to take everybody together, this is something which needs to be explained. So what we'll be doing, we'll be learning more about RF engineering in the domain of UTRON or EUTRON. We will not be very much familiar with the MME, but we'll know what's the role of MME is when we'll learn LTE, what's the role of Node B is. So let's talk about UMTS itself. In UMTS, we have RNC. RNC is connected with the Node B. RNC is a radio network controller. RNC has three functions. You can note down the three major functions is mobility control, traffic routing, and traffic integrity. These are the three functions of RNC. When I say traffic routing, the traffic routing between the base radio network and the core network, that's the job, one of the three jobs of RNC. So that was how UMTS architecture was planned. RNC had a very important role. So now what they did in LTE was basically, of course, the air interface technology was different in LTE. What they basically did in LTE was that out of the three functions, which were traffic routing and traffic integrity, they handed them over to eNode B, and only the mobility control function was left to be controlled centrally, and that was delivered to MME, or which is called Mobile Mobility Mobility Management Entity, MME. So the role of this central body MME compared to RNC is much smaller in LTE. And the basic difference between the two technologies, UMTS and LTE, is its air interface. UMTS used air interface WCDMA, and LTE used air interface OFDMA. So these two are totally two different air interface technologies, and which makes the efficiency of the spectral efficiency, noted down this word as well, spectral efficiency of the two technologies entirely different. And why the companies are going from UMTS to LTE is basically because of the higher spectral efficiency. We should as RF engineer all understand that spectrum is a very, very important resource in RF engineering or cellular network engineering. The more efficiently you can use the spectrum, the better network or the better throughput you can give to the end user. And that is the one of the most basic reason we see the progression that we were using AMS, then GSM, then UMTS, and then now LTE, and we are talking about advanced LTE already, because the technology is progressing and more spectral efficient technologies are being adopted. So far the LTE is considered to be the most spectrally efficient technology, which means it can deliver highest data throughput to the end user, in simple words. So now we understand the two architecture of the two technologies we'll be covering. Besides DAS, DAS is not an air interface technology. For your information, you guys should remember that it's not an air interface technology. It's a signal distribution technique. You cannot even call it a technology in itself. It's a technique or a repeater in itself. So what DAS essentially is a repeater, but to deploy it is very strategic. It's very costly, and it requires a lot of design consideration. That's why this has become a field in itself. DAS stands for Distributed Antenna System. We'll be discussing that and understanding the basics of DAS and macro sites during this session. So within this session, what we'll understand how the overall course flows, what is DAS, what is macro sites, and how they are designed and how the process works. That will be the part of that course in the sessions to come. But what part of our knowledge will be covered mostly in this session, and how part will come in the sessions to come. What and how goes together, but in this course you will have a good understanding of how this course will be delivering you all the body of that knowledge. Okay, so coming to the process. So if I simplify the process, means highly simplify the process, you can easily say that any RF engineering of cellular network, whether it is UMTS or LTE or DAS or even GSM, the old legacy technologies, they have basically three major steps in the design process or the planning process. So design or planning in RF engineering are used interchangeably. When you go more, then you'll find some of the companies have design department separate and planning, but it's very rare. But design and planning is basically the word used interchangeably in RF engineering. So what is the step one? Okay, there is a preliminary design, then there is a radio frequency design sheet, RFDS, and then the third step or the final step of any design process is R&D CIQ. Or radio network design customer information query. Okay, so these are the three fundamental steps. Nobody can disagree. It's generally or vaguely these are the three major steps of any design process of a cellular radio network of LTE UMTS or DAS. Now if I go into the detail of each of these boxes, you will able to see that it looks something like this. So how the RF design process looks like. So basically what I can say is these are three boxes represents the, not exactly but vaguely, the three steps. This is, you can say, step one. Okay. Sorry guys, I'm having problem with using this drawing tool. This is step one. For this, I would say that till here it is step two. And this portion itself is step three, which was described over. So if you are able to see what is this step, what do we have overall over here? So basically this portion is not the design portion. Once you are done with the R&D CIQ portion of the course, you will see that scripting is not part of RF engineering, and where we come in play is basically after this portion, which is somewhere over here, and we call it pre-launch optimization. So basically design cycle ends essentially at when the R&D CIQ of a site is done. Okay, so when the R&D CIQ of that any site is done, we are done with the design of that site essentially. So now before I move any further, we'll go to each of these sessions. You can see over here we have a design requirements. We everything starts with our design requirements. The design requirements come in from the budgeting team uh, or the team which is planning or budgeting the whole network. So, and the standards like what kind of coverage is required is part of the design requirement. What kind of quality and what kind of throughput is required is part of the design requirement. When the design requirements get in the tool, we are able to calculate for a given city or given place the number of sites. That number of sites is basically a rough number estimate, which is usually part of a nominal design. You will see people using these terms somewhere or somewhere not. So, which is basically a part of nominal design. This design is even before preliminary design, and what is it's just ideal design, and the main purpose of that design is to have idea of number of sites, so it can be budgeted, because budget is very important for any commercial activity. So they need to estimate what is the cost to provide a given quality of service to the user. So they do a preliminary design work that's usually is done at the national level and not at the market level. That comes to the market level later on, in fact. So when the design requirements and number of sites is calculated, the overall design is comes in. Where is the most mass of the job? So that design requirements and the budgeting is done by very few people. They are usually very much experienced. So it's done at a very high level usually. Where the market role comes in, or most of the RF engineering job which you see in the market posted comes in, are basically when that design, which was an ideal design, has to be implemented. Okay, when it has to be implemented, if the ideal design said, okay, the height of the site is 30 meters, but actually when you go to a site, it's on a rooftop, and you cannot install a tower, and it's 15 meter. So then you have to adjust the site. You have to accept it or reject it or adapt to the site requirement. So you have to actually redesign the whole site and put it according to the site. Then you do a detailed survey and tell what is possible or what is not possible. So we had a design requirements, we had the initial design. After that, we went actually to the site survey. And when we did the site survey and found what actually we can install or we cannot install, we reach a final portion, which is the RFDS, final RFDS. But before that, we have a portion which is called preliminary RFDS, which is a part of the design. So at both the stages, we should remember we are using planning 2, which is Atoll, Ibwave, or Asset. Well, I got the question, can I explain more the site surveys? I will explain the site surveys in details when we will be doing the RFDS preparation, how the RFDS is prepared. So what are the inputs from the site surveys, what we are looking at site surveys, that will be later part. Right now, I'm just trying to give you guys a good grasp or bird's eye view of the overall design process. And then what we need to do, so you have a bird's eye view of where we will be going. So we have a preliminary design. We will be learning about Atoll and Asset and Ibwave. So Ibwave is a DAS design, is used for DAS design, but also in DAS system, we still have a preliminary design based on the design requirements. And when this design comes in, we have a RFDS based on that design, and then we put it in the planning tool again. So we had a preliminary design, which was essentially ideal. It did not have any information. We went to the site and we found that what is actually is, we start preparing the RFDS and put it in our planning tool. If it meets our design objectives, that becomes automatically final design. But if that's not the case, our design objectives were not met, then we'll go and put the data again in the Atoll, and we'll replan it and we'll run some iteration. When it meets our design objectives, we'll say, okay, all the coverage or throughput and the quality design objectives are met. And this will, based on that, we will prepare our final RFDS. RFDS is radio frequency design sheet. Once the RFDS is prepared, that's the second last steps in the domain of RF engineering. But RFDS basically what it contains site information, azimuth, height, all those details. It contains what kind of node B we will be using, what will be the antenna which we will be using, what kind of remote electrical tilts we will be having. But it does not contain some of the information like what PCI we will be using, what frequency exactly we will be using. That is not usually the part of RFDS. RFDS contains more about the site information like node B cabinet type, the height of the antennas, the feeder length, the feeder types. When I say feeder in RF engineering is basically the cable connecting the node B with the antenna is called feeder. So all those things are part of RFDS, but the soft parameter like frequencies, the scrambling codes, the PCIs, those are not part of RFDS. They are planned separately, means PCIs and frequencies are planned separately, and they are entered into the PCI, PSC, etc. And they are input into the RND-CIQ. And what basically is done, many information is input from other planning sources, in which we will be learning what are the other planning sources in this course, into the RND-CIQ, and we have a lot of information which goes from RFDS into the RND-CIQ. Then we have a complete RND-CIQ. What RND-CIQ itself is, basically, RND-CIQ is basically a way to translate the information of scripting to the scripting team or the UTRAN engineer. That UTRAN engineer or scripting engineer or integration engineer, how to program that node B or the radio base station, which can be node B or eNode B for UMTS and LT, how to program that. All that information is captured in the RND-CIQ by RF engineer and send it to them, and they understand that document. That document is essentially an Excel sheet in a standard format, nothing else. It's an Excel sheet in a very specific format, which the scripting engineer and node B engineer can understand and script or program the node B according to it, or generate the scripts according to it. What RFDS is basically. So the main purpose of RFDS is to communicate with the site construction engineer, how to build the site, what kind of node B will be there, site installation engineer and site construction engineer, what will be the tower height and all those details. Using this RFDS, we communicate all the information about the site construction and installation to the construction team or installation team or site integration engineer. Okay, so basically RFDS and RND-CIQ are the ways of communicating with other departments by RF engineer, and they have to be in a standard format for other people to understand. There are many formats. During the process, we'll be learning what are the formats of RFDS. Of course, and one more thing, RFDS for macros, each of the site is different, separate document. Similarly, the RND-CIQ as well. But for macro and dash site, you will find that there is a hugely different process to reach or the final RFDS of a macro site and a dash sites. They are entirely two different processes. But RND-CIQ still is very similar for a macro site and dash site. Why and how, we'll discuss it in this course when we reach those topics. I received a question, what is PCI? If you understand, PSC is a primary scrambling code. It's used in UMTS, right? It's basically tells you, identifies or separates UE or the mobile equipment or the cell phone in UMTS identifies a cell based on cell ID and the priming scrambling code, or PSC, right? Similarly, in LTE, PCI is physical cell identity. This is basically very similar to what you can say is PSC in UMTS. No, PCI is just like PSC in LTE. Basic is basically used in GSM, and PSC is more like frequency or ARFCN, you know, in GSM. If you want to make an analogy, it's an analogy. Accurately, PCI does not represent a frequency band. In GSM, ARFCN represent a frequency band. So PCI is basically a convoluted code using which UE or user equipment or mobile phone or cell phone identifies a cell, an LTE cell in LTE. So essentially that is, we will learn all more detail later on. So once this whole process is done, we send it out all the information to the Node B engineers. They script it, they construct it, the construction team constructed you based on RFDS, R&D CIQ team, the scripting team based on R&D CIQ script it. Sometime R&D CIQ team also requests for the RFDS for this scripting purpose, but that is not the essential requirement by them usually. And then they script it, and then they'll let us know, okay, we have integrated the site, come and audit. So then the RF engineers' jobs again start, which is called pre-launch optimization over here. Okay, so it's pre-launch. Pardon my writing. So this pre-launch optimization is how it's done. It's totally different topic, different subject. It's another course of pre-launch optimization. Again, pre-launch optimization of macro site is done entirely differently than the DAS sites or the distributed antenna sites. Whenever I use the word macro site, which means tower site or the rooftop site, we will see a lot of pictures in this presentation to come, that how we do it. So basically, we have already explained what are the fundamental steps. These are expressed in words. Fundamental steps of framework of radio network planning remains same irrespective of for macro or DAS sites. The framework or the end-to-end steps which we discussed earlier. Also, fundamental steps of radio network planning remain same on both LTE and UMTS. The steps remain same, but design methodologies and the process between and technological considerations. Technological considerations, I mean, what is the signal level, how the signal will be distributed, all those things. They have a very big difference in case of macro site and the DAS site. In case of LTE and UMTS macro sites design, the design methodology share a lot of similar processes, similar technological considerations, but they are still not exactly same. You cannot say LTE and UMTS. Process is very similar, but not exactly same, because design considerations, the technology considerations are different in many important ways, in fact. Okay, we, as a part of this course, we also introduced to the different terminologies used in different operators within USA. So we were talking about the preliminary design and the final design, how it's done. Okay, can you guys give me a second? I have. Okay, sorry guys. Okay, sorry guys. So basically, what are the fundamental steps? So preliminary design, for example, in AT&T it's called PICD, and final design is called ICD. Uh, PICD, I remember what was those words, but I skipped the acronym. Later on, I will find out and tell you once again what is PICD and ICD. But these are the terminologies. We are in our process. We are understanding it's a preliminary design and the final RFDS. But when you go in these organizations, they have made their own terminologies according to their requirements, and they use those terminologies. For example, AT&T use PICD and ICD. But if you go into T-Mobile, they have altogether different approach to it. The process is still the same, but the approach is a lot different, and they don't emphasize on preliminary design. They directly reach ICD or the final design or final RFDS. How do they do that, and how they can do that, and why AT&T is not doing that? Uh, it's when you understand the whole process. By the end of the course, we will discuss this topic based on different operators in detail. Why different operators are doing different things differently. Okay, so that will be one of the main objective of our course, is to give you understanding of different approaches followed in the and different terminologies used in different operators and vendors as well. So till here, I tried to explain you how the course will work, what is inside the course, what will be the approach to our course, what is the design processes, and our course is basically based on radio network design process. Overall, we will be going step by step through the topics, detailed topics. And if you guys have any questions, feel free to ask the questions. Okay, what was the stage channel capacity, spectrum, fuse, sprinkles, etc.? Are they part of RFDS? Okay, in the design process, the capacity and the channel determination is done. Uh, Capacity is done at the time or before RFDS. What is the capacity requirements? Based on that, RFDS is determined, because capacity requirements affect the design itself and the RFDS. So capacity requirements and the channel requirements are determined in terms of RFDS, yes, before RFDS is prepared. The PCI or the PSC is usually planned after the RFDS is prepared. Ali Hatem, yeah, for sure. We'll be sharing a lot of training materials. We send you guys the prerequisites, and there will be a lot of training materials for you to come during the course. And there will be a lot of tests at the end of each course. Even that at the end of this course, there is a around 50 or 60 question test, which you guys will be taking. We will discuss at the end of this session how you guys want to take the test. You guys want to take the test at your own time or the end of every class, so we can manage, but the test is already there, and there will be a lot of training materials which will be coming during the course. And between the breaks, or between the two sessions, you will have the training material and you will have the test to given online at your own time, at your own pace, but you'll have to complete it within the before the start of the next session. So we know the evaluation, what is the progress, what is the concern, and what is your understanding for each of the sessions. So at the end of this session, we'll have a test as well. Okay, so let's go to some of the RF basics of the course. Why I included this in RF basics? Because for many of you guys, it will be very easy things you guys already know. Many of you guys, it will be new. So the reason I put it in there is to bridge that gap between the students or the audience of this course, that everybody understands what we will be learning in the other sessions of this course. So rest of this course will cover the basics. It's very important because it gives you very good insights of how the macro sites and the dash sites looks like, what are the basic technological consideration do we consider, and what are the terminologies we have. For a few of you guys, maybe you already know, but for those who don't, it's very important. Especially, there will be a lot of things which any of you guys probably don't know if they are not already in the field. Okay, so we have again discussed that there is a nominal phase before the design preliminary phase, which is used for budgeting, or the RFQ, or RFQ is request for quotations, or request for proposal is RFP. If you start working on that domain, which is a higher domain of budgeting and preparation, or RFP or RFQ, you can at the end of this course, if you know what is the consideration in that part of the design, which is before usually, then those consideration is passed on to the markets, or the to prepare the final RFDSs. The thing is, this budgeting, RFP, RFQs, or nominal design is done at a higher level. But as an RF engineer, we should have a good understanding. But there are very experienced engineer you'll find working at that usually national level in those fields. The reason being for that is it requires a lot of understanding of how the things are done in the field before you can reach that level and prepare the budget to reflect the actual cost of the any network deployment, and evaluate different quotations from different vendors and all of those things. And basically, once that is done, that is sent to the markets, which comes for us to prepare a preliminary design, which is PICD, and then the final design, which is ICD. Okay. So, but there are many inputs which is coming from there for your overall understanding that some of the things you will find in these organizations are part of the practice or already decided and they are being followed. Why is that? Because there is a lot of work which has been done centrally or at the national level for those practices to be adopted. And these practices keep changing as well, ongoing, but initially let's say if a operator comes in, he has a UMTS network already, he wants to deploy LTE network, he will not just go in and start deploying LTE sites. He will come in and he'll see where he has to cover. So he will divide his plan in the phases, which cities he has to go, what coverage requirements he has, what kind of throughput he wants. Based on that, he will theoretically plan his network using, again, initially on a micro or Excel sheet, then he will put those sites on a atoll and then see what is the coverage and to prepare for the budgeting or nominal design. Once they are finalized with the budget and they say, okay, we have that amount of money and that many sites we are going to deploy, we are comfortable with it, they request for quotations from different vendors. The vendors comes in, they say, okay, we will deploy the sites. They negotiate the pricing. Once the pricing is negotiated, they negotiate on the process, how they will deploy the site, how will be the design, and then they send that to their regional teams or the market teams, and then market teams say, okay, we have to deploy 1,000 sites. Big cities have more sites, small regions have smaller sites, number of sites. So that number of sites usually come in. That number of sites is variable within the range of 5 or 10%. That is already done centrally by the national team, and those number is being followed. So rest is basically implementation. For that, the number of sites are there, the ideal design or the nominal design is there, then the market or the regional teams work on it to make a preliminary design, and that preliminary design, then they work again, as I was explaining in this process earlier. Remember, this process diagram is very important for you guys to understand in detail. So preliminary designs then is also done by the regional teams or market teams, and then they prepare initial RFDS, they put in and everything looks good, they put in the final RFDS, and that's how the things goes. But there are many considerations which are coming from the central team or the national teams. We should understand that. So we have to work in that scope of work which has been already been given, and the practices which already been adopted or communicated. So that's how the overall process works. The open end of the process was the central team, which I tried to explain the role of the central teams over here. I hope that's well explained. Are there any questions in this regard? You guys can type in. Okay, if you have questions, you can keep typing, and as soon as I see the question, I'll reply the question. In the meantime, I'll move to RF planning basics. Before we dive into the details of the planning, again, as I said, we will go into some basics. We have already sent the prerequisites of this course. Many of you guys were able to read it. Some of you don't. In any case, if you didn't read it, you can even read it after this session between now and the next session. So I expect you to go through all of it, every one of you, between now and the next session, and understand what's going on in that. Some of the basic concepts which are so basic that if you don't understand them, then you won't be able to continue the next session. I have tried to explain over here, so we don't have any hoops or the gaps in the next session. So what are the basic concepts? So as we say, do you guys want a break for 5 minutes? Because after every hour, we should have a 5 minutes break. So we have reached 11. We'll have a 5 minutes break, or make it a 10 minutes. At 11:10, it's 11:02 already. At 11:10, we will come back. That is exactly after 8 minutes, we'll be back. So guys, I will be stopping the recording for that moment, and see you in 10 minutes. Go freshen up, grab a tea, and then come back. Thanks a lot. So, yes. So what we were going through was our RF design basics. Now, we'll be going through the basic concepts. Some of them will look like how the sites are, what are the micro and dash sites, what is to give you a very good feeling before you jump in. So it's very easy for you guys to grasp the course material to come. So what is, for you guys who already know the concept of path loss, it sounds boring, but few of you guys, definitely it's a new concept. So we are talking about the RF engineering, right? RF engineering is a radio frequency. What is a radio frequency is? It's basically a electromagnetic signal. How it's generated? It's generated by an electrical signal. When electrical signal passes through any transponder, or transponder means anything which generates the form of a signal, or which is antenna. It passes through an antenna and it converts an electrical signal to an electromagnetic signal, and antenna also converts electromagnetic signal into an electrical signal. So basically, when antenna generates a signal, okay, we will go through the antenna concepts once. If you guys can see the material which I sent, I specifically sent you guys antenna theory document, which covers antenna. Because if you don't understand antenna and all those things, it will be really, it's a prerequisite of this course. So basically, whenever there is a signal, it has a loss. So it has a loss because of the distance between the transmitter and receiver, which is free space path loss, which is represented by this equation, which you can see over here. So this is a simple equation of free space path loss. Okay, one of the biggest challenges of RF design engineering is to predict a signal as accurately as possible. What will be the signal level at a given location away from a node B or E node B tower. So that is a very big part, and that's why we use ATOL or planning tool like ATOL and Asset for macro sites or Ibwave for DAS or in building sites. So this is one of our biggest challenge. So there are a lot of theoretical calculations which has been done. There are a lot of theoretical models which have been developed to predict. So one of the most basic thing which tells is a free space path loss is if your transmitter is in front of you and there is a straight line of sight, what will be the signal if you transmit 20 dBm, what will be how much signal you will receive at the receiver at a given distance is governed by this equation. Okay, I will just explain you two things. You can see in this equation, if the distance is higher, your loss will be higher, okay, based on distance. And if your frequency is higher, your free space path loss will be higher. Okay, so remember that those things. If the distance is higher, your free space path loss will be higher. If your frequency is higher, your free space path loss will be higher. Okay, so you will. What it means is when you send a 20 dBm signal at the receiver, you will receive, let's say, minus 5 dBm or minus 8 dBm. If your frequency is higher, distance is higher. So to give you a empirical sense that how it works, for example, if your distance is doubled, you will have a 3 dB higher loss. If your distance is half, you will have a 3 dB better signal. If your frequency is doubled, if your frequency is doubled, then you will have a 3 dB higher loss, free space path loss. If your frequency is halved, let's say if you are transmitting a signal at 800 megahertz, you have for example, you have a loss of 20 dBm. At 1600 megahertz, you will have a loss of 3 dBm higher. You will have a loss of 23 dBm. The question was why 92.45? Then again, you will have to go how this equation is derived. So if you have been doing, how this equation has been derived, then you can only understand why it's 92.45. It's complete. If you know how different calculation like the Newton theory of gravity equation is derived, all those details are like what is actually okay. How I can explain? Okay, I'll be able to explain in next slides, I believe, more this concept even better. But that's a mathematical equation which governs it. What is propagation? So the signal transmits from transmitter to receiver. Analogous situation. No, this equation is not valid for non-line of sight, and that is what is our challenge is. If it is line of sight, then we can predict the signal strength more accurately. But in our environment of RF engineering, there is hardly any time line of sight between the mobile station or the BTS or node B and the UE or the cell phone. So that's the biggest challenge, and that's what we will understand in the next slides to come. So we don't have a line of sight, so the signal reaches us as a free space path loss. If we are standing in front, the signal reaches us as a reflection, as a diffraction, as a shadowing. So signal before it reaches from the transmitter to our cell phone, it goes through different phenomena. Okay, and what signal strength will we receive is it's very difficult to predict, and that's why these planning tools are so popular, like Etoll or Asset. And not only you'll find these planning tools are very popular, you will see that these planning tools have different propagation models, and there are companies which have and their job is to make a more accurate propagation model and sell it to the operators, and the operators run those propagation model, test them, and see how accurately they are predicting the signal level in their different environments, and how to use them. One thing more which is very important is we should all understand is propagation is overall, it includes free space path loss, it includes diffraction, reflection, and everything. So we need something which does not only cover a tool which does not only predict based on the free space path loss, but also other phenomena of radio propagation, which are reflection, diffraction, and others. Like I'll jump to this slide, then I'll go back. So you see, this is a base station, this is a UE. What we have is a direct side, there is a diffraction, which you can see. Okay, let me check spot. So you can see there is a direct line of sight, there is a diffraction, right? And also there is a reflection. So all these phenomena are called propagation. In general, all these phenomena which through which signal is received from a transmitter or base station to the UE, it's called propagation. And all the different paths it receives is called multipath. So a signal is propagating from transmitter to the UE on multipaths, and this phenomena itself is called propagation of a signal. Okay, propagation of a signal from a base station to the UE. Does any of you have any questions or so far? Feel free to type it in. Multipath fading. Okay, now what is multipath fading? It's not fading. Fading is basically happens when this is multipath. Now, if the signal at the receiver do a constructive interference, it will gain. If it is a destructive interference, then destructive summation, then the signal will fade. So it can fade, it can enhance itself. Usually the effect is 3 to 6 dB because of multipath in the propagation model, and the propagation model have to predict it more accurately. Signal can diffract. Okay. I got two more questions over here. Signal can diffract or reflect from any material? Yeah, but based on the nature of the material, the amount of signal which is diffracted or reflected will be different, but signal can diffract or reflect from any material. For example, water is considered to be a very, very good reflector. If you are throwing a signal on a water, you can see that signal somewhere like 50 or 60 miles away sometimes as well. And that has been experienced. So the sites which are planned across near the water, they are tried to be captured, especially in Manhattan, where the Bay Area, it's very difficult to control the sites because the sites start to overreach on the other side because water is a very good reflector. Is there refraction phenomena occurs? Refraction is a phenomena as well, yeah. But usually refraction does change the path of light. The refraction happens when it starts when signal is traveling through a medium which has different densities at different portions. Usually in the atmosphere, that's not the case. So refraction is the phenomena, but I don't think so in a propagation model it has a very big impact. But good propagation model, because learning a propagation model and theories and what are different propagation models, it's a science in itself. If I let you guys know water bodies is between MS and node B, is there refraction phenomena occur if the water bodies is between? Well, refraction, if it'll reflection will occur from the water bodies and node B. Refraction, water will the signal will go inside the water, yes, but if the signal goes inside the water, it's means it's a lost signal. So there is a portion of the power of the signal. It's not a complete signal. We always mean signal means a portion of the signal will go as a result of a refraction inside the water, and some of it will be reflected out. The one as a because of the phenomena of refraction, because water is a different medium and air is a different medium, and when it hits the water, some of it will be refracted inside the water and some of it will be reflected outside it. So the one which will go outside will go back to the atmosphere, and the portion which will be go inside the water will be lost anyways, that portion of the energy of the signal. Because remember, it's energy of the signal we are talking about. Complete signal is never lost, is not lost. It's the energy of the signal is lost when it hits the water, because some goes inside the water and some is reflected by the water. So, and how much is refracted inside the water? I don't know. We'll have to go through some studies to do it. But most of the energy is reflected by the water, because water is a very good reflector. How much is refracted? It's less, because the studies and my personal experience or everybody's experience will tell one thing, that water is a very good reflector. If you if you're throwing a signal or your antenna is pointing towards water, then if water is continued for 50 miles, maybe you will able to see that signal after 50 miles because of the good reflective nature of the water. So now going back to so we understand what is a propagation is. Propagation is basically we should able to predict is how the signal is transmitting from the base station to the UE, but how this signal is combined and what will be the received signal level, then there is a lot of theories around it. Okay, there is a lot of theoretical models which try to predict the signal level if it is transmitted from a base station, what will be the signal level at the UE. There are multiple base stations around each other in neighbor vicinity of each other, so what will be the signal level from each of the base stations. There is a lot of theoretical work which is being done, and it is a work in progress till today, because you will find like AT&T have a project which is called suburban project or rural project. What basically it's doing, they bought a new the propagation model. That propagation model was integrated with their planning tool, which is ATOL or ASSET, and they use that propagation model to predict the signal level more accurately inside. Yeah, so those propagation models, what they basically do, if you understand the radio propagation environment, you will find that there is a terrain or terrain, how you pronounce it, is like hilly, or the land is going up and going down. How is the terrain? Is it a flat terrain? Is it a hilly? Is it a mountainous? There's one thing. Then on the top of it is a natural vegetation. It has a trees, it has a grass, it is land, and over that there is a man-made structures which is called clutter. Okay, so there is terrain, then there is vegetation, there's a man-made structure, and overall all these three things makes a clutter. Okay, so what is our clutter basically? Urban environment has a different clutter because there are more man-made structure. Rural is a different, suburban is different. So you should understand there are different clutters. It's a rural, urban, suburban. So whenever you say a propagation model, you will also see a thing called tuning. tuning your propagation model. So most of the propagation models needs tuning. Means at least all of the ones I know. So there are at least tens or over 50 propagation model, but we will just discuss two of them, which are the most popular of them, and they're very basic propagation models. So there are very advanced level of propagation models. If you guys want, you can go and study. But so each propagation model is tuned what's tuning means that every propagation models take some inputs to predict the signal. That those inputs depend upon the terrain, vegetation, and the man-made structures, buildings, homes, skyscrapers. That's called clutter. So each propagation model is tuned according to its clutter. Okay, so there are urban clutter, there are suburban clutter, there is rural clutter, all those things. So it is tuned according to that. So what is clutter? Clutter is basically the environment in which the signal is being transmitted and received. Is it an urban environment? Is it a suburban environment? Is it a rural environment? Is it a dense urban environment? Yeah, so these are the basic general classification of clutters: urban, rural, suburban, dense urban. You will also see hilly clutter tuning as well. So you can classify according to the needs, special needs, icy or Arctic clutter as well. You will find it like if there is ice everywhere in this mountainous area, there is ice, or it's a plain land like Antarctica, or it has ice. It needs to have its own propagation model according to that. It needs, no, sorry, let me correct myself. It has a propagation model, but that propagation model has to be tuned according to that clutter. So there can be many propagation models, but every propagation model is tuned according to that clutter. Some of the propagation models are designed for a specific clutter like urban or suburban itself. So some of propagation models are designed for a particular clutter, but many of the propagation models are tuned for that specific clutter. Model tuning itself is a subject. You'll find the jobs of model tuning itself, RF engineers doing the model tuning. All those things comes before the network deployment usually. We will discuss some of it later, some of it further. But let's jump to